Hello everyone, my name is Ovidiu Cătălin and today I'm going to talk about 17th century and modern single-lens refracting telescopes. This is my first presentation about this field and I'm very excited to share with you all my knowledge about these instruments. First things first, look at these impressive replicas of 17th century very long refracting telescopes. Quite impressive indeed. Now let's talk about the most important component of these instruments, the objective lens. And we have here some original 17th century objective lenses used for these instruments. These are refracting telescopes that use lenses, and in particular they use a single lens to collect the light, called the objective lens. More about this in the following video.
A ray of light traversing the surface, separating two mediums of different density, is refracted, that is, deviated. But light is composed of various colors, and the angle at which the colors are refracted differs for each of them. For this reason, in a positive lens, the light rays do not all converge exactly at the same point, but the radiations of shorter wavelength focalize closer to the lens and those of longer wavelength further away from it. This phenomenon is known as chromatic aberration. The lack of a single focal point provokes a phenomenon of iridescence, which significantly impairs the quality of the images. Already the first telescope makers had empirically realized that the effects of chromatic aberration in a telescope substantially diminished when the ratio between the focal length and the diameter of the objective was increased. 17th century telescopes, in fact, not only had relatively long focal lengths, but were also usually fitted with a diaphragm to reduce the aperture. But the focal length required to limit the effects of chromatic aberration is not proportional to the diameter of the objective, but to its square. If, for example, an objective with aperture of 2 centimeters shows no appreciable chromatic aberration for focal lengths of at least 75 centimeters, an objective having double the diameter, i.e. 4 centimeters, must have a focal length 4 times greater, or nearly 3 meters. This circumstance profoundly conditioned the subsequent evolution of the telescope. On the one hand, progressive increase in the diameter of the objectives led to the construction of increasingly longer telescopes, to the point of reaching the practical limits of fabrication.
Now let's talk about the early 17th century lenses, which are very strange. Let's take an example. A single lens with a short focal length suffers from huge chromatic aberrations, and the only way to reduce this is to increase the focal length. But this is not all. Look at the right. The glass itself has many problems. Also with the manufacturing of the glass, the fabrication of the actual disc, down to the grinding and polishing. Most of 17th century early objective lenses and eyepieces were polished and ground at the middle, so only the middle part of the lens is used. Also, longer the focal length, thinner the lens. Look at these examples in the right and the left. These are early 17th century lenses, eyepieces and objective lenses, and also this is a focal test of an objective lens, and you can see the actual shape of the glass, the actual problems. This example is a huge lens. Many of these 17th century lenses were very big, only the middle part is used, so the rest of the lens is left alone, and only the middle is used, the good part of the lens. All 17th century refracting telescopes have diaphragms to reduce the aperture. In addition, these scopes used not one but many diaphragms with different apertures to reduce the chromatic aberration. This effect blurs the image, and the only way to tackle this problem is to make many diaphragms and then test them which one produces the sharpest image possible. You can see the chromatic aberration effects on this image. Now let's talk about another subject, How these lenses were made, objective lenses and eyepieces. All of this starts with a glass plate, with a piece of glass. All of this involves a piece of glass. This glass is cut into a blank shape, into a disc. In most cases, thinner glass is used, and then the glass is ground using emery powders and other assortments of abrasives on a metal tool. The actual tool is curved. Another method is to glue the lens on a handle and use this support to actually grind the lens on this tool, on this metal tool that has a desired curvature depending on the radius of curvature you want to achieve. And many of these tools have very small curvature. How they achieve to actually make this curvature is unknown. This is another method using a support for the lens. Different abrasives are used, starting for the largest abrasive to the smallest emery powder. And this process actually generates the curvature of the lens. This is how they do it in the 17th century. This is how spectacle glasses were made. Apply this to the telescopes and this works. Many opticians in the 17th century have invented their own methods, which mainly were improved, and many opticians have taken their secrets to the grave. Now, how these tools look like? We know they are made of lead. We have some examples of these actual tools. These are the tools used by Giuseppe Campani to make its lenses. They have different radius of curvature, starting from flat ones for flat surface up to convex surfaces for eyepieces, objective lenses, and also I think they have convex surfaces for concave lenses. They are used manually and others are attached to a machine, which were hand driven. More about this process in this video.
The glass was made by melting siliceous sand with soda and other ingredients. A disc, called a blank, was cut from the block of glass, and its edge was shaped and smoothed. To produce convex lenses, concave lenses, or other types of lenses, the disc was ground with a metal bowl whose surface was of the desired curvature. Abrasive damp emery powder was applied between the glass and the bowl. Other, much finer powders were used for the final polishing. In the 17th century, the masters of this process were Eustachio Divini and Giuseppe Campani, whose lenses were valued throughout Europe. Scientists such as Christian Huygens or Evangelista Torricelli often made their lenses themselves. Machines for semi-automatic lens grinding were designed. Until the 19th century, however, the best lenses for optical instruments were handmade. Only those for non-specialized use, such as opera glasses, were machine-produced.
Now let's talk about the polishing of the actual surface. This involves probably the same tool used for grinding, but the actual method is quite unusual. For this process they use a cloth, mainly deer skin, and then they pour some very fine abrasive called tripolo or tripoli onto this deer skin or cloth, and then they polish the lens. How the cloth actually molds itself to the tool, it's unknown, and this is the actual limitation of this process. You need to have a perfect match of the cloth and the actual tool for this process to work. And the technology is very limited from today's standards. And at the end of the 17th century, many opticians produced very fine lenses using this method. How they achieve this is unknown, because this process is very limited. You need to have the perfect match between the cloth and the actual tool to be perfectly matched for the actual surface to be polished evenly to achieve a good optical quality. And this is the limitations of this process. Now we're going to examine some lenses made by Giuseppe Campani. These are the actual blanks cut out from the actual piece of glass. Look how dark they are before grinding. And now we're going to the grinding stage. Look how transparent the glass is. You can actually see the curvature of the lens, the actual convex shape. And now to the final stage, the actual lenses. You can see now the difference between the plate glass and the newly polished lenses. These are quite impressive progress. Now we're going to talk about the construction of the telescope, the tube and the mount. First of all, the first instruments were handheld. You can actually hold it in your hand, and these are the simplest. Draw tube refracting scopes from the 17th century, down to refracting telescopes that have a very long focal length, starting from 2.5 going up to 4 meters long. The telescope is mounted on a straight board to prevent the actual optical tube from bending under its own weight, and the instrument is quite portable, up to 2 meters long. If you increase the focal length going up to from 4 meters down to 5 meters, it becomes unstable because of the actual length of the optical tube. These telescopes had limitations, but these are very small instruments in comparison with the largest instruments from that era, mounted on a very complicated setup that involves two-point mount. You have a mounting system that involves ropes and pulleys to actually orient the telescope, and a mounting setup at the eyepiece. These are very huge instruments, and the slightest breeze can actually produce huge and powerful vibrations. These were practically the limit of construction, up to 50 meters long, and the two-point support system is good for telescopes starting from 2 meters up to 4 meters long. The same method we use today for our single lens refracting telescopes. These are Huygens drawings of different mounting systems for his telescopes. Now we're going to pass on to the aerial telescope, the instrument without an optical tube. We have an objective lens mounted on a high pole, and the actual lens, it's aligned using a rope or a string mounted on a system, or the eyepiece is handheld. You can hold it in your hand and try to find the actual object you're looking throughout the objective lens. This is the actual replica of the Huygens design at Triel Observatory in France. You can see how complicated this instrument is. You need to align the objective lens, and you need to align the eyepiece with the objective lens. It's much harder, and it's much easier to use the eyepiece in your hand and try to find the object in the objective lens, but also the objective lens must be straight, perfectly aligned with the object in the sky. It's very hard to use, and the slightest breeze can actually affect the instrument if you use a string to connect the objective lens with the eyepiece. These are images of Saturn, Jupiter, the Moon, and double star Castor at Triel Observatory. We have an image of Saturn and the rings. You can actually see the disk. The image is low in contrast because it's an aerial telescope. And we have a picture of Mars with a polar cap. Now we're going to talk about what you see with these instruments. The problem was with these instruments that the actual optical quality is not so good. Many lenses were good, some of them mediocre, some of them very, very poor quality. These are tests made by opticians, and the objective lenses made by Giuseppe Campani and used by Cassini to discover his famous division, and also moons of Saturn. The problem is the homogeneity of the glass, but also the polishing. You can see some focal test and Ronchi test on 17th century objective lenses. This is a focal test on a full lens from a Galilean eyepiece. You can see the middle part is good, but the edge is worse. Only the middle part is good, so this eyepiece had an aperture mask. This is an objective lens made by Christian Huygens, 62 mm in diameter, and this test is conducted at 34 mm in diameter. You can see the lens has many problems. This is an Galilean refractor from the early 17th century, And you can see now the image of a statue with this telescope at 16 magnification. The field of view, it's very small. It's very hard to find objects with this telescope. And we have here an image of a clock 10 meters away with a Galilean scope. Another image of a clock in the far distance with an early 17th century scope. And you can see a picture, a clear picture with a camera, compared with the actual image throughout this instrument. You can see the limitations of these early 17th century scopes, the small field of view, some chromatic aberrations and spherical aberrations. This is another Galilean scope, a much larger one. I think it's about 1.5 meters long. And you can see the image of a church in the far distance. Look how small the field of view is. It's very hard to find objects in the night sky using these instruments on these mounting systems. These were quite unwieldy telescopes. Imagine huge instruments like this with focal lengths of about 50 meters long, 45 meters long that Hevelius used. This is an image of a picture on the wall. And you can see some chromatic aberrations and spherical aberrations. This is a handheld refractor, very small instrument, but it produced good images, probably in the middle of the 17th century when the optics were better. These are good images with a very small pocket-sized instrument. And now this big monster, Giuseppe Campani, very long refracting telescope, up to 6 meters long. You can see some images throughout this instrument. You can see clearly chromatic aberrations, but the images are good up to 86 magnification. Quite good instrument at the middle of the 17th century. Quite good images. The optics improved. This is another 17th century telescope, an image. I don't know what this image is, what it represents, probably something in the distance. These are simulations throughout Campani objective lenses used by Cassini to discover its division. I conducted some testing with these lenses. This is a certain simulated image throughout an aerial telescope used by Cassini. And these are the actual objective lenses from the Paris Observatory made by Giuseppe Campani, and some testing that I done with also from 4 different apertures using these aerial telescopes. Quite good lenses. I'm impressed with the quality. Even the actual process of making the lens is quite mediocre, but the quality is almost modern. It's quite impressive. This is the lens used by Cassini to discover the Cassini division. It was some debate because the lens had huge aperture, 137 millimeters, but at 85 millimeters is quite good. So probably this lens was reduced with an aperture mask because it's impossible to see the Cassini division at this huge aperture. This is the actual lens, and you can see the middle, it's more scratched than the edge, so this lens was probably reduced with a mask. This is a polychromatic test of Van Huygens objective lens, 85 millimeters and 90 millimeters long. You can see the good images, quite good at this aperture. Saturn is very great. These are Ronchi test and focal test on Campani objective lenses. You can see the middle is very good, but the edge is worse. This is almost close to the modern performance of a refracting telescope. Almost, not quite good, but close to modern refracting telescopes. Now we're going to talk about modern versions of these instruments. And the first example is this monstrous Hevelian refracting telescope made by some Japanese. It has an aperture of 6 inches and a focal length of 21 meters long. It takes a team to actually assemble this monster. This is probably the most impressive telescopes on Earth, the longest instruments ever made in this modern era. The optics is far better than Hevelius had in the 17th century, of course, but the mounting, everything is close, very close, almost a copy of this 17th century telescopes used by Hevelius. Is quite impressive, using ropes and pulleys to actually move the whole telescope. You can see now the objective lens of this immense refracting scope, and some pictures of the moon throughout the Hevelian scope. I remind you that these pictures are pre-processed in Registex for some detail enhancement. Now we're going to talk about TAVI's optical instruments, these modern versions. This is a 40mm, 2.4 meter long single lens refracting telescope replica. Very good optics on a 2-point system, one at the middle and another system to hold the back of the telescope at the eyepiece to prevent the actual bending of the tube. These are cardboard tubes. The only problem with them is the humidity that destroys them over time. So he built, after some time, a modern version using an aluminium tube, everything made out of metal. This is the new version, 38mm refracting single lens telescope, high quality optics. You can see the actual instrument, everything is made of metal. This is a modern version of early telescopes. We have here pictures of the moon with a 40mm scope. Quite good images. Now we're going to talk about the process of making the lenses. He uses Beka 7 plate glass and also window glass, tested before to see if the glass has some defects. And then he grinds the lens on a concave mirror using abrasive. The same process we use to make mirrors. And then he polishes the lens on a pitch tool, the same curvature as the concave mirror, with cerium oxide. And then he tested the lenses, the small focal lengths, with an artificial star. And then he uses plain mirrors to test the long focal length lenses. And these are his completed objective lenses with very high quality. We have here a piece of glass that he converted into an objective lens. Very interesting to see a piece of glass turn into an objective for an astronomical telescope. This is a lens cell for the 38mm refracting scope. Everything is made of metal. The craftsmanship is quite impressive. You can see the pictures of the moon throughout the 40mm long scope. Jupiter with a great red spot. This is quite unique. These instruments are very long. Many amateurs say they are not good for planetary astrophotography, but these images are quite the opposite. Planetary photography can be done with this scope. And also you can see the sun using a Bader Polar Soil. And now to my instruments, my homemade 28mm refracting telescope. The objective lens is made by TAVI's Optical, and the optical tube, it's made out of copper. It looks like an old Alvan Clark refractor, quite impressive. And this is a picture of Albireo with this instrument. And double stars are the most beautiful objects you can see with this instrument. These iridescs are so amazing at the eyepiece that they're so beautiful and perfect. It's a quite unique experience at the eyepiece because of the actual aperture and the long focal length compensate and makes a very nice iridesc on bright stars and double stars. This is my favorite scope for bright double stars. We can see the pictures of the moon using my 28mm refracting scope and an ASI ZW camera. Quite good detail for a 28mm refracting scope. These are high resolution pictures of the moon because the long focal length is huge and you cannot see the full moon. This is the picture of Saturn throughout the 28mm. You can see the rings and the space between the rings. Venus with this scope. And the shadow of Io on the disk of Jupiter. Animation with this instrument. And the Great Red Spot transit. You can see the Great Red Spot above. Almost 10,000 frames each. Some pictures of Jupiter. You can see the bands of clouds. Quite good detail of the bands with a small scope. Very nice instruments. I made this telescope myself. Everything is handmade, only the mount is commercial, it's an AQ1 mount. These are pictures made by Tavi using his 28mm scope. Very nice details on the moon, using small aperture. This year I made a very long 35mm 2.1 meter long refractor used on the Dobsonian mount. It was very shaky scope, it's big, but I give it away because it was too long and the vibrations were so worse. And after this one I decided to make a new instrument using a Tavi's optical lens, 34mm in diameter and 1.8 meters long, the successor of the 28mm. It looks like a huge Alvan Clark refractor. It's quite the most beautiful instrument I've made this year, and it's probably the last mounted on an equatorial mount. The vibrations are not so strong if you wield it carefully. This is a picture of a sunspot. You can see the granulations on the sun using the new instrument. Everything is handmade. The lens cell is made out of copper, the focuser made out of copper, everything is metal. And I worked the whole day to assemble the telescope, from the objective lens cell to the baffles and the focuser, everything to the mounting on the equatorial mount. You can see the sun live throughout this instrument. This is my aerial telescope version, mounted on some tables. The actual objective lens is put on that very straight board, and with an eyepiece far away in the distance you can actually view the objects with an handheld eyepiece. The diameter is 60mm and the focal length 5.5 meters. You can see the sun projected on the paper without an eyepiece. And these are the lenses made by Tavi's Optical, a 42mm lens with a 33mm aperture and a 60mm diameter lens. Made from Beka 7 glass, great quality. The 60mm lens has a focal length of 5.5 meters. It's a very long focus, high quality objective lens. Single lens, biconvex symmetric shape, and this is the system that I used for solar projections and visual observations on the moon and the planets on an aerial system. That board, that straight board, it's used for movements, mounted on a Dobsonian mount, and on top we have the objective lens. I have many objective lenses, starting from a 3.5 meter long focus down to 5.5 meters. It's a very usable system because it can be very easily aligned. It's very hard to mount on different tables to get it on the right position and the right height. Only objects up to 45 or 40 degrees can be viewed with the 5.5 meter lens. It's very good. We can see the objective lens, and by making solar observations, especially solar projections, without an eyepiece, I don't use eyepieces, just the single lens element, you can see many details on the sun. Even the details in the penumbra of sunspots, the sunspots, faculae on the limb of the sun, and many other extremely nice details on the paper if you have a screen to project the sun. It's very, very high quality lens and the details are amazing. The magnification is about 30x, 25 magnification if you project the image on the screen. And you can use the aerial system to look at the moon using many eyepieces, especially using a 32mm eyepiece 171x with a large 5.5 meter long telescope, 60mm in diameter. There are very nice clear images of the moon, very nice details, absolutely amazing. So these observations are very strange. You can see it's completely different from today's standards. The actual mounting system, the images, you can see an image of the sun using a 4-meter long focus lens, 26 millimeters in diameter. You can see the actual system with a meniscus lens, a 4-meter long focus for solar projections. It's very good, but I used a very long focus lens with a large diameter to see many details, to obtain many details on the sun, because size matters. These are incredible instruments. You can see the actual setup using many tables to put the objective lens on that board, and it's very easy to move. You can walk on the stair, climb the stair very easily, and align the lens with the sun. It's very easy to align because the board, it can be a viewpoint for trying to align the optics. It's a very important aspect of this system, but I try many different aerial systems using Huygens method on a pillar, and it takes about 10 minutes to align the actual lens with an object like the sun. So with this system it's fast. In 1 minute I can align it with the sun, and it takes 5 minutes to set up the whole tables. It's very fast assembly. The problem is I cannot go higher because it's unstable, but it's good for objects up to 40 degrees in the sky, so you can wait for the moon to set and get lower in the sky, so you can make observations with these lenses. The images are very clear if you want to make solar observations using the projection method without no eyepieces. The level of details are amazing, and the moon, it's quite spectacular. It's superb. The only problem is trying to align with the planets and the stars, because they are a single point. Even the planets are very difficult to align with this lens, because farther you go from the lens, the higher the magnification is. So you try to put the object in the lens, but the lens magnifies the image, so it's very hard to align the object with the glass. So in a sense you need the objects to be in the center of the field of view of the lens, so you can view the object with an eyepiece. And if you move slightly, the object goes away, disappears from the field of view. That precise you need to be to actually view stars and planets. Also, it's much more harder to align the lens, but focal length does a great job, because longer the focus is, the less need to collimate or to be precise with the alignment. So almost a 5-meter long lens, it looks like a flat lens if you view the actual objective glass. And the longer you go, you don't need to be so precise when it comes to collimation or trying to align perfectly the lens with an eyepiece. This is the sun viewed throughout the 26mm 4-meter long focus lens. It's amazing. Another great method of observations with this single lens is to try to project the image of the moon and try to observe the moon with no eyepieces, directly with the lens. People that have myopia, that suffers from myopia, and like me, I have -4 on both eyes. When I take my glasses off and try to focus the actual image of the object with the single lens, I get a magnified image, and I see the projection in front of my eyes. You can see here I defocused the camera lens and try to make observations with the moon using a 3.5-meter long lens with a 26 diameter aperture. Just the lens and the camera. The camera is defocused, so you can see the surface of the moon projected in front of you. It's quite an amazing experience. And longer the focal length, the greater the magnification and the actual details, it gets more and more precise and finer. The image is about, let's say, 30x, 22x, something like this. Using this method, you can see the peaks on the middle of the craters. This is just the camera and the lens, nothing else. It's quite amazing to do these experiments using single lens. So no eyepieces involved, just my eye, the same thing I see throughout my eyes. No eyepieces involved, just the lens and your eye. So the eye becomes an eyepiece. Especially for people that have myopia and suffers from this affection, you can do these experiments. It's quite an advantage. You can see now the lenses made by Tavi's Optical, the 36 and the 60mm sets. And now you can see the solar projections with a 5.5 meter long lens. You can see the diameter of the sun in comparison with a human finger. It's quite huge, the sun, in the image. The level of details it's very nice when you do this method with no eyepiece, just the lens projecting the image of the sun onto a paper. The sunspots, the penumbra, the details in the penumbra, the faculae on the limb of the sun, all you can see with this method. And the image of the moon using an aerial telescope, a tube support system with a 40mm Plossl eyepiece, the 60mm 5.4 meter long focus. The images are quite spectacular. The system that he uses for this photography, it's a 2-point support system. The objective lens is mounted onto a straight board, and the board is positioned and also supported by 2 points, a ladder and a tripod. The system is very shaky, so the aerial method, it's much more efficient than that. The actual board can flex, so it's very hard to photograph. These are testing of the lenses using a plain mirror, the soda lime glass, window glass, for defects, and these are testing of the 60mm lens, showing the quality of the glass. So this is it, my fellows. It's time to say goodbye, and I wish you clear skies, and I hope we meet next year for another presentation about these early telescopes. Bye bye.